save it with a new name. I'll select the raft and so view 3D, replicate it at +10. Where the original is deleted. View. So I have defined the properties first. So I'll use area sections and add a copy of the section, and that is the bottom slab of the slab. Let's say we are using a 500 millimeter slab as the bottom one, or say 450 millimeter thick slab at the bottom one, 0.45. That is the bottom slab. Top slab, we'll use 250 millimeter, 200 millimeter top slab, because we need to have 2 mats of reinforcement in the top slab as well. And we'll add the web walls of 300. So we are going to get web walls of 0.3 millimeter, the 300 millimeter thickness. So we are having the walls of 300 millimeter thickness. So what I can do is, first I can say this is going to be 200 millimeter thick top slab. Sign. And that is the top slab of 200. So you can have a look at it. At this height, we have the top slab, and we consider that we are going to have a thickness of 1.5 meters. Otherwise, it's difficult to work inside. So we say we are going to have a overall thickness of say 1.8 meters. And the advantage is that will remove some soil, and it will compensate for part of the weight of the structure. So we'll say that, we are going to have either 1.8 meters or 2 meters. I think 2 meters might be easier. So we say that, we are going to have a thickness of 202 meters. But if you are, when you consider the center, that is 450 and 250. So we say the distance between the top slab and the bottom slab is 1.5 meters. The distance between the top slab and the bottom slab is 1.5 meters. And when you add the thickness of the top slab and the bottom slab, it comes closer to 1.8 meters. 1.8 meters. But the distance between the top slab and the bottom slab is 1.5 meters. So which means I'm going to replicate this at a depth of minus 1.5. I made a mistake because I deleted the original. So I'll undo it. Ask it to select, get the previous selection and replicate with the same thing, but this time I'm not deleting the original object. Yes, here you get another plane. So if you view this level, I think we have not created it properly. So what I do is I'll go back to this level. I'll undo it. Display. Right. So what I do is I'll select this, replicate, minus 1.5 once. Now you can see the bottom slab has appeared, and I'll view it like this in 3D. Now you can see two planes are there. So now I have to create these additional planes, and to do that I'll get some guidance by looking at show selection only, and I'll go 3D, and now I have a good idea about where the walls are. So what I do is this one, I'll go with y equals 0. Y equals 0. And I can use this. Before that, before doing all that, I have to allocate the bottom slab thickness to the model. So go back to this one. Then select this, assign area sections, and that is the bottom slab 450. And then I'll say deform shape. And then I'll select view 2D, y equals 0. And so I will have the pipe cap, top slab, bottom slab, web walls 300. So I'm going to create the wall. So I can replicate that. At 7.5 3 times. And then I can select this. Select that. Select this. And replicate. At 6. 1, 2, 3, 4. 4 times. And then I can select this and replicate 6 one time. And I can select this, replicate 6, 6, 12, 12 and 18 and 24. 12, 18 and 24. And I can have the wall here also. So that means I can replicate it 4 times. Oh yes, I can replicate all these because I have not continued the lift shaft walls. So right, I can replicate these also 4 times. Replicate 6 4 times. Right, and then I can select x equals 0 and I'm here and I can replicate that. Replicate at 6 3 times. And then select all those and replicate that direction at 7.5 4 times. So now we can ask it to draw, show all. Before that, we can turn it around and see whether we have got it right. Yes, we have got it right. So you can see right round, it looks okay. And when you look from below, you can see that we have got the walls in all the directions. The length looks okay. Yes, lengths look okay. Yes, all those lengths are okay. So now we have got the whole sorted out. Here you can see all these walls. The web walls are all okay, but there's a problem. So what we do is we'll ask it to show all. Okay. Now we have the top slab divided, bottom slab divided. So what we can do is can select one of the elements and see how to divide as a trial. And we can say 3 and 6 and see what happens. That's not the way we want to divide it. Do. divide areas 6 and 3. That tallies with the way that we have divided. So what I can do is I'll go back and I'll go to 3D view, 3D, and what I can do is I can enlarge this area and select all these elements, and in doing so I'll be selecting all the elements in both directions. So you can see the elements in both directions have been selected in one go. And then what I do is ask it to edit the areas in this ratio. So this is okay. And I can view y0, and I also can also view x equals 0. So you can see it's all divided properly. So what I can do now is this 3D view. This side is 3D view. And this is at a height of 8.5. So I can select all. And replicate. At minus 8.5 once, and delete the original so that I can bring all back to the ground level, so that the raft will start resting, cellular raft will start resting on soil. So now the cellular raft is resting on soil. So now we can analyze it. Now you can see the very marginal change in the natural period of vibration, very marginal. And in this particular soil, we are having this weak patch as well. Weak patch is also there. So that is the structure which has the cellular raft, and you can see the deformation, and you can see the center of the structure sinks little more than the rest of the structure, which is something that you get in the shape of the deformations. And then what we also see is that we can view the Z0, where we get the bottom slab. I was not expecting that. Unlike 64. We look at the top slab. I think it's we are looking at the wrong slab. Z equals 0 is the bottom slab. Z equals 1.5 is the top slab. That is the top slab. Top slab. Top slab moments are in the range of 50s and 60s. $100. I was expecting a slightly different result. Here you get 1035. And bottom slab we should be getting much higher moments, unless we have made a mistake in modeling. Z equals 0. View, define, view, 2D, backface, 0. That was we are getting fairly low pending moments. That's why I'm wondering why we are getting very low values, 140s, 122. Because there's a stiff element here, and we look at one of the ribs and see what's going on. We say y is equal 0, and we'll ask it to show. Now it's a shell element in the vertical plane, so we might have to look at F11 and F22, F11 diagram, combination 4. They are connected, and here you get a negative force and a positive force. So there's tension here and compression here, and compression here as well, tension. So it's bending this way, but I'm not very convinced that why we are getting so low values for this one. So M22 diagram, 1-1 diagram, and M12 diagram. Let's see what that one. That is also low. Solids, clear section. Let's have a look at the section. We have a section here. In this section, we'll see frames, cables, combination 4, axial force. Okay. We are transferring an axial force of 4,122. So it's a very large axial force that is coming. 4,500 and so on. So it looks okay. And then we are getting solid elements. Service combination 4. S33. This is the weaker region that we are getting some problem. And other locations we are getting some values like 199. Because now we have to some 200. There's a weak pocket here that is not transferring the loads. That looks okay. And in a pocket, this pocket we get something like 190. But when you go down, you can see due to the weight of the soil, it's increasing. So there's some stress transfer here due to the rigidity of the foundation. But only thing that I'm not convinced is why we are getting when Z equals 0, why you are getting so low moments, deformed shape due to dead. So you get 53.6 millimeter deformation. and shells combination 4 and 1 due to dead. What's happening? 35, 72, display shells not dead, Winx, understandable, very low effect because lateral loads are small, and then when you go with combination 3x M11, okay, so the moments are like 108, 101, highest. This is the reason why we get these values. First, we'll see what is the shear we get on this. We'll have a look at the shear force as well. Shells V13, 35, 146. So we get some high shear values at certain locations, and we are getting M23. Yes, high shear values, especially close to the rib. Close to the rib, we get high shear. In the center, we get low shear. So these are the rib areas where we are getting high shear values. That looks okay. And then we have to look at shells. An M22 value, which is the bending moment in this direction, we are getting a bending moment of 140. And this is actually a local value. The reason is here we are getting a rib. Here also we are getting a rib. Here we have a rib. Here we have a rib. So what actually happens is these moments are the moment values that we get in the bottom slab, because these are cellular raft. So in the cellular raft, we get a bending moment of 126, and some places we get 111, 130, and 120. And here I saw 140 somewhere, say 130. And the thickness of the slab is only 450 millimeters. So 130 into the power 6 divided by 1000 divided by 400 as the effective depth squared, 375 squared, because you need higher cover. So you get a M over BD squared value of 0.92. So these values are correct, because these are, the reason is here we get a rib, here we get a rib, those are rigid areas, and those rigid areas are transferring the loads at concentrated values, whereas these are a slab which deforms more. So because of that, the slab is subjected to a lesser load. So the loads are on the raft, the soil is actually acting with patches, and because of that reason you get under the rib higher stress, within the slab lower stress, and then if you look at the top slab, and that is Z is equal to 1.5. Most of the locations here you get very low values because it's not subjected to very high loads, except the loads that are coming from above. But there can be some additional moments due to the deformation because we have a weak patch here. And then other locations you get a moment of something like 104. But in this particular area, what actually happens is we have some of the shear walls supported on the top slab, because we did not create additional shear walls, additional partitions in the under the shear walls. So, for example, if I take this and then say all, take this area and ask it to show only the selection and go for 3D. Show all. View 3D. If I select this area, so you see that the top slab is supporting the shear walls here. That's why you get high moments in this area on that, because we don't have internal partitions in this area. That's why you get high values for bending moments in this area. And then here also you might get some high values, and here no problem, because the shear wall is directly over the supports. So this way you can actually get the bending moments in the top slab and the bottom slab. And bottom slab will need bottom slab moments are okay. And then when you look at the distribution of the soil pressure, that also goes into concentrated areas, because the deformation of these ribs will be lesser than the deformation of the slab. So the soil pressure under the raft will not be perfectly uniform. But overall, you can see it actually gives us a clear idea about the variation that we can expect. And if I say show all, and then ask it to go for S33 under service conditions. On this particular plane, you will get a variation like this. But if you look at the other side, y equals 24. And ask it to display solids, S33, service, COM3X. Here you can see that weak pocket effect is not there, and the moments are, the stresses are in the range of 170, that range. The stresses are in the range of 170, and that particular effect is not there, whereas in this particular diagram, which is where the weak pocket is available, you can see these stresses are higher. The soil stresses are higher than the location where the weak pocket is not there. So this way, you'll be able to get some idea about the stresses that occur on soil, in addition to the stresses that will occur within the structure. So this is the way you can actually model a cellular raft, and the sometimes the total weight of the cellular raft, we generally expect it to be lesser. And the main advantage of cellular raft is you can actually embed it within the soil, so that part of the weight of the structure can be compensated by using a cellular raft. So it's like having a basement. So if you have a basement, you can actually model it this way. If you can create the basement in a similar manner. Whereas in the case of a basement, you may not have all the partitions, but you will have a slab. But you might have a thicker raft at the bottom, and then the void. And because we are removing part of the soil, then that weight can be compensated for the weight of the structure. So that's the advantage of a cellular raft.